Hello everyone, welcome to our exploration of queue-based load leveling design pattern. As designers, we always seek well-established and elegant solutions to common problems. Cloud design patterns are those elegant solutions for the cloud, instantly enhancing your applications with proven methods for scalability, security, and cost efficiency. In this video, we will discuss a problem, present the design pattern solution, and implement it in a real-life scenario. Whether you're a developer, an architect, or just someone curious to know about this design pattern, this video will provide you with valuable insights. My name is Madhur, let's get started. Let's begin by setting the context and understanding the problem where you can apply this design pattern. Cloud solutions often involve running tasks that rely on various services. However, a service subjected to intermittent heavy loads can lead to performance or reliability issues. A service can be part of the same solution as the task that uses it, or it could be a third-party service providing access to frequently used resources like a cache or storage service. When multiple tasks use the same service concurrently, predicting the volume of the requests the service may receive at any given time can be challenging. This unpredictability can cause a service to experience peaks in demand, which may result in overloading and slow response times. Furthermore, flooding a service with a large number of concurrent requests can cause contention and lead to service failure. To solve this problem, we can use the queue-based load leveling design pattern that involves introducing a queue between the task and the service. With this, the task and the service can run asynchronously. The task posts a message to a queue. The queue acts as a buffer, storing the message until the service retrieves it. In this way, the queue decouples the tasks from the service, and the service can handle the messages at its own pace, regardless of the volume of requests coming from the concurrent tasks. This pattern provides the following benefits. First, it can help to maximize availability, because the delays arising in services won't have an immediate and direct impact on the application, which can continue to post messages to the queue even when the service isn't available or isn't currently processing messages. Secondly, it can help to maximize scalability, because the number of queues and services can be varied to meet demand. Thirdly, it can help to control costs, because the number of service instances deployed only has to be adequate to meet the average load rather than the peak load. Now let's go through some considerations for implementing this pattern. The first consideration is to implement application logic that controls the rate at which services handle messages and avoid overwhelming the target resource. This can be accomplished by inserting an application between the queue and the service that can throttle the messages being passed on to the target. We will elaborate on this further when we discuss the real-time scenario. Secondly, message queues are a one-way communication mechanism. If a task expects a reply from a service, it might be necessary to implement a mechanism that the service can use to send a response. Another consideration is that the pattern can lose information depending on the persistence of the queue. If the queue experiences a crash or drops information, it is possible that you may not receive a guaranteed delivery. Your queue's behavior and system limits must be considered based on your solution's need, and necessary strategies should be adopted to increase resiliency. This pattern is useful to any application that uses services that are subject to overloading. On the other hand, this pattern isn't useful if the application expects a response from the service with minimal latency. Now let's take a look at a scenario where we can apply this pattern. A very common real-life scenario is when multiple instances of a web application are running simultaneously and writing data to an external data store. The data store can become overloaded, resulting in issues such as timeouts, throttling, or other type of failures, which can prevent the data store from responding to requests promptly. Many teams try to increase the capacity of the database to handle peak loads, but it might not be the optimal solution as it increases costs. To address this issue, we can deploy the queue-based load leveling design pattern. If you're using Azure, we can deploy Azure Service Bus Queue. For AWS, we have Amazon Simple Queue Service or SQS, and we can also use Kafka if we want to implement a cloud-agnostic service. This will help distribute workload evenly between the various application instances and the data store. To do this, an app can be used to read messages from the queue and perform read-write requests to the data store. Again, we can use Azure Function, AWS Lambda, or deploy a VM to run our custom application. By controlling the rate at which the custom application passes requests to the data store, the application logic can prevent the store from being overwhelmed. In this way, this pattern helps minimize the impact of peak demand on availability and responsiveness of both the task and the service. If you found this video insightful, do share, like and subscribe. Until next time, stay curious, stay data driven.